And welcome back, everyone. Happy rainy day. I hope your studying is going well this week and that you're managing all of your labs and tutorials and learning some cool science along the way. So we're now exploring transition metal complexes. And last class, we learned that these complexes are really important in different materials development, but also in our bodies, where a metal can be part of a protein. It's surrounded by small ions or small molecules to make a complex. Sometimes those molecules and ions are part of a large ligand, like EDTA, or they could be part of a protein. So iron has multiple stable oxidation states. It could be iron 2+ or iron 3+. And in cytochrome C, iron exists as the metal cation surrounded by different amino acids that are part of the protein. And iron 3+ can gain an electron, become iron 2+, and it's part of the electron transport chain in ATP synthesis. We learned about EDTA and how it's an important chelating agent. So if you have heavy metal poisoning, you can very carefully, under a doctor's supervision, undergo chelation therapy. So here's an example with the heavy metal cobalt, and we can see cobalt is attached to 6 donor atoms, so oxygen and nitrogen in EDTA. So the cobalt is the dark blue atom there, and we can see that this EDTA connects at 6 different points and completely surrounds this metal cation. And so we can say it has a coordination number of 6. So lots of important applications with transition metal complexes. We learned about how to name transition metal complexes, what the square brackets are about, how to calculate the oxidation state based on the number of different types of ligands. Remember that a ligand could be an anion, like chloride or hydroxide, or it could be a neutral molecule, like water or NH3. Well, today we're going to continue down our analysis of transition metal complexes and look to see how we can have different arrangements of ligands and metal cations and how that results in different types of important compounds. So today we're going to be looking at a bunch of different isomers that result from the unique combinations of transition metal complexes. So isomer, you've heard that word before, usually in the context of organic chemistry, often with like hydrocarbons. We have lots of, like millions of different organic molecules because we have so many different isomers. Isomers have the same molecular formula, so the same total number of atoms, but somehow they're different. And we have a whole variety of different types of isomers. Same molecular formula, but different somehow. If it's a constitutional isomer, it's different based on the connectivity. So whether it's straight chain carbon or a branched chain hydrocarbon, those would be constitutional isomers. You've heard of cis-trans isomers, and today we're going to look at a variety of isomers that have to do with transition metal complexes. So the first one that we're going to look at is a linkage isomer. So we're going to try to tie the name into what it means. When we have a ligand, ligands that have more than one donor atom could be part of a linkage isomer. So if we look at this nitrite ligand, we can see that it has a lone pair of electrons on the nitrogen. It could donate that lone pair of electrons to an orbital in the metal cation, form a complex covalent bond, sort of like ionic, sort of like covalent, and it could combine with nitrogen being the donor atom. Alternatively, we could have the oxygen behave as the donor atom, where the metal connects with the lone pair of electrons on the oxygen atom. So depending on what the donor atom is, we could call it nitro O to tell everybody that it's connected at the O atom, or nitro N to communicate that we have a different isomer, same molecular formula, but that bond is between a different donor atom. Now it's the nitrogen. So we could have another type of ligand, thiocyanate. We can see that the nitrogen has, actually I'm going to leave that one for a second. The sulfur has a lone pair of electrons, and that sulfur could form a bond and coordinate with the metal cation. So we could call it cyanato S because it's connected at the S atom. Well, we could take one of those lone pairs of electrons on sulfur and turn that into a double bond, and take one of the pairs of electrons that's making a triple bond and turn that into a second lone pair of electrons on the nitrogen. So then nitrogen would have two lone pairs of electrons, and carbon has two double bonds to these different atoms, to sulfur and nitrogen. And now nitrogen, with one of its lone pairs of electrons, could form a bond with the metal cation and coordinate through the nitrogen donor atom. So we can have different types of complexes depending on the donor atom of a given ligand. And this pentaamine, so that's 1, 2, 3, 4, 5 amines, nitro-N, it's connected at the nitrogen atom, cobalt-3 complex is this really cool orange color. But if you change anything, change one of the ligands, change the bonding atom, the donor atom, change the metal, it changes to a completely different color. And we're going to talk about that in topic 4.2. Welcome to those of you who are arriving. Okay, so that's linkage isomers. The donor atom that is the linking one is what makes this complex unique. Okay, now we're going to move on to coordination isomer. Coordination isomers are because the ligands that are coordinating around the metal cation have swapped. So here we have cobalt coordinated with 6 amines. This is the first coordination complex. Here we have a coordination complex ion. It's a cation, and it is connected to the anion that is also a coordination complex. So we have our cation complex and our anion complex. When we go to make the coordination isomer, the cobalt is now coordinated to the oxalato ligand rather than the amines. And the chromium, rather than being coordinated with the oxalato, is coordinated with the amines. So the metal cations have swapped places. They're coordinated to the other complex's ligands. So we can only really do this when we have a cation complex, an anion complex, and the metals trade places. And this makes for a pair of coordination isomers. So we still have a cation complex, an anion complex, but we've swapped what is coordinated between those two isomers. Okay, number 3, and I will admit, the names can sometimes get a little bit mushy, so come up with a strategy to be able to distinguish between these different isomers. So rather than coordinating around different metal cations, now we're looking at the counter ion, so the ionization isomer. In the one on the left, we have a coordination complex with platinum, and bromide, or bromido, is the ligand in the complex on the left. We also have 4 amine ligands, but we don't really care about those at this moment. On the left, the bromide is the ligand. On the right, the bromide is the counter ion. On the left, chloride is the counter ion. On the right, the chloride has become the ligand. The counter ion has swapped for a ligand So these are ionization isomers. The counter ion has swapped. And this would be considered a pair of ionization isomers. Okay, so those are 3 isomers to get us started today. And now we're going to dig into the coordination number. So the number of donor atoms that are bonded directly to the metal. Now notice that this is not the number of ligands, because in this case we have 1 ligand, and we were introduced to EDTA last class, where EDTA is connected to the metal cation at 6 different bite marks, 6 different donor atoms. This is a hexadentate ligand. It bit it 6 times. Even though it's 1 ligand, it had 6 bites. It has 6 donor atoms. But if we were looking at the coordination number for this complex right here, the coordination number would be 6, because it has 6 donor atoms connected to that central cation. So be careful whether you're talking about coordination number, the number of donor atoms, or the number of ligands, because those aren't always the same. So a nice little review here from last class. Which of the following directly describes this complex here? Chat with the person beside you, break down the interpretation of this complex name, determine the oxidation state, and the coordination number. Yes, how can I help? Ooh, usually the cation goes first, then the anion. Is that what you're asking? Oh, so if you have multiple different types of ligands around the cation, I think it's alphabetical order usually. I think so. Yeah, I'm pretty sure it's alphabetical order. You can get into some nitpicky rules. I'm 90% sure it's alphabetical. Yeah. And 10 more seconds. And 3, 2, and 1. Okay, most people went for C, but only half the class. So let's break this down. So here we have sodium as our counter ion. Na plus is not surrounding the platinum. The complex is in the square brackets, and that's what we talked about last class. So it's the chloride ions that are our ligands here. So the Cl negative are our ligands. They're anionic ligands. They're negatively charged. Sodium is our counter ion. Sodium, each one has a +1 charge. That's the cation. So therefore, our coordination complex must have a -2 charge. Or you could look at the entire compound having a neutral charge. So having 2 sodiums, each with a +1 charge, plus whatever the oxidation state of platinum is, plus 6 chloride ions, those are our ligands. That was one of the ligands that we mentioned in our table. So 6 negative charges, 2 plus charges, that gets us to -4. The entire compound, the complex anion and the sodium counter ion, comes to a charge of 0. Therefore, platinum must have an oxidation state of +4. So that's half the battle there. Then we also need to remember Roman numerals. I won't ask for show of hands on who remembers Roman numerals. Oops. Roman numerals here. V equals 5. If the 1 comes before the V, that's 5 minus 1, which is 4. If the 1 comes after the V, you add it, and that is 6. So we also need to brush up on potentially Roman numerals. So platinum 4 is the correct option here, but we had 2 answers that had platinum 4 as the oxidation state. So then we have to figure out the coordination number. So we need to identify what's our ligand and what's the counter ion, because we can ignore the counter ion for now. It's only the ligands that are surrounding our platinum. And by the end of today's class, you will be able to even draw this out like this. So we're going to see that we have 6 chloride ligands, chlorido ligands. We have 6. Each of these is monodentate. There's only one possible donor atom for each of these ligands. So therefore, each of them is surrounding this chloride. So therefore, we have a coordination number of 6. It's connected to 6 donor atoms, our 6 chlorides. Okay, so we only had half the class going on that. Do we have any follow-up questions on this before we move on? Yes?
Like how many areas it has in the table, because it's 60, you could use that as well. Because it's 80, you could use 60. We know that the space is.
Okay, so the question was, can we also use the electronic configuration for platinum, seeing where it is on the periodic table, how many d electrons it has to figure out the coordination number? No, yes. No, because there are lots of exceptions. Sometimes the d electrons behave as valence electrons. Sometimes they behave as core electrons. So sometimes they participate in bonding, sometimes they don't. So we can't always predict it. That's a great question. So the answer is not really. For our class, we can't, and we're not even going to try, because we're going to find that sometimes we can reasonably predict the shape, and sometimes we can't. And we're going to talk about that in just a minute, but that's a really good question. It does have to do with the d electrons, but it's not always cut and dry. Any other questions about what we've done on this slide here? Okay, so let's keep moving. So we know how to solve for the oxidation number, and now we're looking at coordination numbers, and we're going to look at a bunch of examples, so this should become more apparent as well. So we're going to start with a coordination number of 2. This is when we have 2 donor atoms that are complexing with our metal cation. Now, the number of examples of complexes with a coordination number 2 is quite minimal. This is not a common one. Here we have an example with silver plus as our cation, and we can see it's coordinated with 2 amino groups, so 2 amines. Now this particular complex is known as Tollens reagent, and it's a common experiment that you may have done in high school to add Tollens reagent to an aldehyde or a ketone solution. And depending on how Tollens reagent reacts, depending on how this complex reacts, you can draw a conclusion if that unknown solution had an aldehyde or a ketone. Aldehydes are readily oxidized by this complex. So aldehydes will react, and the Ag plus will be reduced to Ag, which is solid silver, and you get this silver mirror forming on your test tube, and that tells you that that test tube was containing an aldehyde functional group. If it contained a ketone, well, you won't get that silver mirror because this complex won't react, and it doesn't react with the ketone. Struggling with words here. So silver plus can form a coordination number of 2, copper 1+, and gold 1+, but that's kind of it for complexes that only have a coordination number of 2. It has to do with their size, it has to do with their valence electrons and where they're placed. If you look on the periodic table, you'll see they're all in I am struggling with words. What's the vertical thing called? Row, group. Thank you, group. They're all in the same group and they can form a linear complex. So if a coordination number is 2, it typically has a linear structure. If we have a coordination number of 3, it is typically trigonal planar. Now notice that we're using the words usually, typically, because there can be some wonky exceptions because you're in the transition metals. But if we have a coordination number of 3, typically those ligands are going to spread themselves out, those donor atoms, and give us a trigonal planar arrangement. Ooh, one of the really cool ligands that we haven't talked about yet that comes up in these different types of complexes is triphenylphosphine. And so here on the left with our gold, and then with our trigonal planar with our copper, we have triphenylphosphine, and I want you to be able to recognize it and know what it's talking about. So it's written with phosphorus. There's our phosphorus atom. You can see the phosphorus has a lone pair of electrons. That's what it donates to the metal to form the complex. That's the donor atom. Phosphorus donates the electrons. And then we have C6H5. So 1, 2, 3, 4, 5, 6 carbons, 5 hydrogens. And you can see we have 3 of them connected to the phosphorus. So it's quite a large ligand. It's not just like a one little atom, it's multiple atoms for our triphenylphosphine. And this ligand is used in all sorts of different applications in organic synthesis and pharmaceutical drugs and in stabilizing different plastics. So you're going to see it come up in a lot of examples. Our researchers in our department use triphenylphosphine in a lot of their experiments. Okay, so coordination number of 2, linear, that matches our VSEPR understanding. Coordination number of 3, trigonal planar, that also matches our VSEPR predictions. When we get to coordination number of 4, it gets a little bit wishy-washy, and we can't actually always predict the shape based on the coordination number 4. Now, based on VSEPR theory, we would expect if we have 4 donor atoms attached to the central atom, we would expect it to have a tetrahedral arrangement. And in a lot of cases, in some cases, we certainly have that tetrahedral arrangement. However, it's also possible that we could have a square planar arrangement, which means we probably have some non-bonding electrons in there, but it's hard to predict. If we just know that the coordination number is 4, can we predict whether it's square planar or tetrahedral? Not really. We have to experimentally determine that for coordination complexes. Depending on the size of the metal cation, the size of the ligands, there are some trends that we're not going to worry about, and you could make some predictions. But sometimes the difference between the stability of tetrahedral versus square planar is so close that sometimes it could even go back and forth. So unless you're told for our course, or you're given hints or clues to let you know which one it is, we can't predict just by looking at the complex formula which structure it has. That said, we have different types of isomers that can arise from these different shapes. And so this could be a clue that helps you out and helps you determine I think I forgot to eat my lunch. That's why I'm struggling with words. If we know something about the isomerism of that complex, we might be able to figure out if it's square planar or tetrahedral. For example, here I have a tetrahedral shape, and it has 2 unique ligands and then 2 other unique ligands. I'm going to call these the A and B. If I had another complex that was tetrahedral with 2 like ligands and 2 identical ligands, and they were both tetrahedral, we would be able to overlap those and see that they're identical. If I moved one of these ligands to a different region and tried to overlap them, I can see they overlapped perfectly. These are not isomers. However, if we have a square planar arrangement, I'd like you to imagine that these two up and down prongs on our octahedral complex are not there. We're only paying attention to the square planar. If the two like ligands are beside one another, that's very different than the two like ligands from being across from one another. These two structures would be isomers. We can't overlap them perfectly. They're different molecules. So if we have a square planar structure, we could end up with cis-trans isomers. Not possible with tetrahedral, as we just played with our model kit, but certainly possible for square planar. One of the most important examples of this is cisplatin. Here we have the chloride groups in a cis arrangement in this square planar structure, meaning they're right beside one another. That's in contrast to the two chlorides being opposite one another. And again, the easiest way to build this is to use your octahedral pink shape in your model kit and just ignore the up and the down electron density regions and just pay attention to the square planar possibilities. So those two ligands beside each other is the cis, and this cis isomer is an anti-cancer drug. The arrangement of the chlorides and the amines is such that it can interact with your proteins in the expected way and can help to fight cancer. However, the trans arrangement, when the chlorides are in opposite arrangements, it can't interact with your proteins in the same way, and it is not a useful drug. So we're on to our fourth type of isomer, cis-trans isomers, and these are possible when we have a square planar arrangement. It's not going to be relevant if it's a tetrahedral arrangement. How do we know if it's tetrahedral or square planar? Well, you don't. You'd have to determine it experimentally. Or if you're told it has an isomer, then you know it has to be square planar. Okay, so we've done coordination 2, 3, and 4, and now we're moving on to coordination number 5. This is when we have 5 donor atoms that are attached to the metal cation forming our complex. Now, according to Vesper, if this was the whole story, we would expect a trigonal bipyramidal shape. And indeed, we do get that some of the times. Depending on what the ligand is and the metal is, it's also possible to have a square pyramidal arrangement. And depending on what the complex is, the size of the metal cation, the size of the anions, sometimes they could even exist in equilibrium. So it could be like going back and forth between these two different arrangements. So again, for our course, I wouldn't expect you to predict which one it's going to be if it's in a complex, because it could actually interchange over time. But we know the options. Okay, and now we get on to coordination number 6, and this is the most common transition metal complex arrangement. This is when we have 6 donor atoms, and then we end up with some interesting isomers in this case. So if all the donor atoms are the same, or all the ligands in this case are the same, for example, if we had amine, 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 well, we're not going to have an isomer for that. If we swap 2 of those NH3 ligands, it's still going to be the same complex. If all of the ligands are the same, except for one unique one, we could put that chloride in a different spot, but that's also not going to create an isomer. For example, here is my octahedral arrangement with 6 donor atoms. If all of the ligands are the same, it's not going to have an isomer. If 5 ligands are the same and one of them is unique, it's also not going to have an isomer, because even if I popped this one over here and put it on the right-hand side instead, all I have to do is rotate it and it's back to the same thing. So 6 identical ligands, or donor atoms, or one unique one, we're not going to have an isomer. But is it possible to have isomers in different cases? I'd like you to chat with the person beside you. Imagine you had a coordination complex. It has 6 donor atoms. They're all monodentate ligands. 4 of them are alike, and 2 of them are alike. How many stereoisomers can you come up with? This question is a whole lot easier if you have your model kit with you. You can do it from your mind, but you can also prove to yourself tonight what the answer is. So chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, before we look at your responses, something I didn't say out loud, I'm sure all of you identified this. If we have a coordination number of 6, which means we have 6 donor atoms, that makes for an octahedral shape, which is why we pulled out our octahedral VSEPR shape. So we would expect the ligands or the donor atoms to be 90 degrees apart all the way around. Octahedral is what we would predict from VSEPR. Transition metal complexes can be weird sometimes. Sometimes you could have a distorted octahedral, where some of these bonds are a little bit too close together or a little bit too far apart. There's another non-bonding pair of electrons around there. We won't be able to predict which is which. So for our purposes, when we're analyzing a coordination number of 6, we'll be looking at the octahedral examples most often. Okay, so our next question, oh, that was not a question. I'm going to delete that one so you don't have to worry about replying to it. Delete that after class. Oh, and now I can't see. Let's see. Here we go for C. C was the most popular. Going for 2, and I agree. So let's go ahead and build these. So I have my octahedral complex. I have 2 identical monodentate ligands and 4 others. So I'm just going to use no colored balls for those. So if I have my first ligand here and my second interesting ligand here, I could put it beside each other, or I could put them exactly across from one another. If I go to overlap these 2 compounds or complexes, I can see that they don't overlap. So we have 2 different isomers here. If the 2 like ligands that are the same are right beside each other, we're going to call that the cis isomer. So here we have chloride and chloride right next to each other. They're 90 degrees apart. That's a cis isomer. However, if the chlorides are opposite from one another, then that will be our trans. So here I have my trans, and here I have my cis isomer. So 2 different possibilities if we have 4 ligands of whatever and 2 similar ligands. Okay, this is going to be a raise your hand question. Let's imagine now you have a complex, coordination number of 6. It has 3 similar ligands, we can call them A. 3 similar monodentate ligands, call them B. How many different isomers could you come up with? So chat with the person beside you. And 3, 2, and 1. Who votes for 0? 1, 2, 3, and 4. Okay, and I would go with 2. So let's see why that is the case. If we have 3 ligands or 3 donor atoms here that are identical, we have 2 ways of making unique complexes. Right now, I'm not seeing any model kits, which is fine. I didn't give you a heads up for that this time. But go home today and prove to yourself that you can't come up with a third or that these are the only ones. So right now, I put these 3 ligands on the same plane. So if you tip it this way, you can see they're on the same plane. If I wanted to draw a plane or connect them, I can see they're all on the same plane. This one is called the Mur isomer. It's like the meridian that goes through our planet. That's where the name comes from, Mur. The other option is if I take one of these and put it such that they're no longer on a plane. 2 of them can be on a plane, but one of them is not. This one is called the Fak isomer, or the face isomer. This one you can imagine is like popping out towards you. The Fak isomer is when all of them are in close proximity, making a 3-dimensional conglomeration. So here we have our chlorides on a plane, making a meridian, or our chlorides jumping out in 3-dimensional space to make our Fak isomer. Okay, so let's wrap this up with a question. What type of isomers are these? And chat with the person beside you to identify why or why not you can rule out each of these. And 10 more seconds. And 3, 2, and 1. No, wrong question. Okay, we have just over half the class going for E. Uh-oh. Okay, I realize these are a lot of terms. I have thrown a lot of isomers and different ways of thinking about complexes. This helps us to understand how we can have so many different types of isomers and what we have to pay attention to as scientists. That said, I realize learning all these terms can be a little bit challenging. So let's see if we can identify what these different things mean. So the answer is E because the issue has to do with what ligand is coordinated around what metal. So zinc around, or amine around zinc, zinc with amine, or zinc with chloride. Copper with chloride or copper with amine. The metal cations have swapped the type of ligands that are surrounding them. So the types of ligands that are coordinating around them. Okay, I'll give you 5 seconds to wrap up your conversation. 3, 2, and 1. Okay, so a quick review. The ionization ones, think about the counter ion. So that's the same word. So if the ion, the counter ion, and the ligand have swapped places, that's our ionization isomer. For cis-trans isomers, that's when we have our square planar, and that's when we have two like donor atoms or two like ligands, where if they swap places, that makes a new complex. Linkage isomers, that's when we have the option of more than one donor atom forming that link to the metal. And FACMAR, what we just learned today, is when we have 3 and 3 like ligands, that's when we have to pay attention to whether they're on the meridian, they're planar, or if they're in that 3D structure like a face. Okay, we're going to wrap up now with a discussion of some very important transition metal complexes. We now know how to name them, figure out the oxidation state, but it's also really helpful to see why we're learning about these. And 3, 2, and 1. Okay, let's look at this tetracarbonyl nickel complex. Here we have 4 carbonyl groups surrounding the nickel, and this makes for a gaseous complex. Metals aren't normally gaseous. Normally they're in rocks or metals that we find in the earth. It's not normal to have a metal that can turn into a gas. But if we can come up with a way to turn a metal, like solid nickel, into a gas, that could be really helpful for refining that metal. So I grew up in Northern Ontario. In Sudbury, there was a metal refining factory, and they used this process previously. So the Mond process is when you can take a metal, and it could be in an impure fashion. So it's mixed with other types of metals and other impurities that we don't want in our final product. But we could react it with gaseous carbon monoxide, and it would form this gaseous complex, and we can see it has a tetrahedral arrangement. Then we can take that gas away and separate it from those solid impurities, leave the solid impurities behind, take our metal complex that is now a gas, and then go back the other way, heat up our complex, get rid of the carbon monoxide ligands, and we end up with pure nickel. And so this is a really important metal purification process. The final example that I want to talk about today is in hemoglobin. And as we started with this class, iron 2+ is a really important transition metal cation that you need in your body. Hemoglobin transports oxygen through your body and brings it from your lungs and out to your extremities. It works because there's this really big porphyrin ligand. Iron can bind to the 4 nitrogen donor atoms in this porphyrin ring. And each subunit of the hemoglobin protein has one of these porphyrin rings that can bind to iron, and the iron can bind to oxygen. So as you know, proteins are made up of amino acids. That, if we just have a big chain of amino acids, that would be the primary structure that's just all floppy. But then those amino acids can form secondary structures, like these alpha helices, those curly Qs, and beta sheets when we have the amino acid sequence going back and forth. And then we can have a tertiary structure where we have these subunits form. And then when we have 4 subunits come together to make hemoglobin, that's a tetramer. It's 4 pieces coming together to make the final structure of our protein. Now we're going to zoom in here to an example of hemoglobin. And we can see in this hemoglobin structure that there are 4 porphyrin units here. And the porphyrin units are actually planar. So as I rotate the protein, look at the black structure. The black structure is our porphyrin ring. The metal binds in the middle of it. And the porphyrin ring is planar. So as we rotate, you can see when we're looking down the plane and when we can look at it straight on. This porphyrin ring, it's drawn on your paper flat because you have a 2D piece of paper. Now we're going to imagine that we take that porphyrin ring with the 4 donor atoms, the 4 nitrogen atoms, and then flip it out towards you. So you're taking that paper, the porphyrin ring, flipping it out, and now above the porphyrin ring, the iron atom there at the top can bind to an oxygen molecule, O2 aqueous, that has been dissolved into your bloodstream. And then below, it can bind to an amino acid in the hemoglobin protein to make up a coordination number of 6. So 4 from the porphyrin, and then when we flip it sideways, we have the up part to the oxygen and the down part to our protein. So coordination number of 6, making that octahedral complex around the iron cation. I have like 30 seconds left or 60 seconds, so just hang tight if you can keep it quiet for that long. Thank you. So hemoglobin can bind to that oxygen. We breathe in gaseous oxygen. It dissolves in our lungs and in our blood as aqueous oxygen, and hemoglobin binds to that oxygen through an equilibrium reaction. We're going to learn a lot more about equilibrium systems in Chem 1302b. If we add more oxygen, you know from Le Chatelier's principle, that pushes this equilibrium. That's why sometimes if someone's in a health crisis, they can take on a higher concentration of oxygen wearing an oxygen mask to push this equilibrium and help their hemoglobin take on more oxygen. Who has a carbon monoxide detector in their home? Hopefully everybody, especially if you have